All right, guys, this is a quick video tutorial on the final two gas laws that we're going to cover, and they are Dalton's law of partial pressure and Graham's law of effusion. Okay, so let's start with Dalton's law. Okay, so this is Dalton's law of partial pressures. This is the same Dalton that we learned about in Unit 2, about like atomic structure and stuff. So he kind of figured out, the initial basics about atoms and bonding and stuff like that. Same guy. So what does this say? What this is this is with gas mixtures, okay? So the total pressure of a gas mixture is equal to the sum of each gas pressure individually. Okay? And so the way that formula looks is it looks like pressure total equals the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, and so on, however many gases are there, right? The reason why this holds true is because of the kinetic molecular theory that says basically that the identity of the gases doesn't matter, right? Because they don't impact each other. The containers are usually so big, the gas particles are so spread out that they're not impacting each other at all. So for example, air, right? Air is a mixture primarily of nitrogen and oxygen. So the total atmospheric pressure is 1 atmosphere, and that 1 atmosphere is composed of pressure from the oxygen particles hitting containers and pressure from the nitrogen particles hitting containers. They have nothing to do with each other, so if you can calculate them individually, then it's really simple. You can just add them up and get an answer, okay? The other kind of cool thing about this law is super helpful in some of the challenging problems because it allows you to do the math for each gas individually and then add them at the end. One thing we also know is, according to the ideal gas law, pressure and moles are directly related. Okay, now that's not like an official law that we talked about, but it's true, obviously. More particles, more collisions, more pressure. So if pressure and moles are directly related, then that actually allows us to use the same fractions. So what I mean by that is, for example, like our atmosphere is about 80% nitrogen particles and about 20% oxygen particles, right? This is air, give or take a percent of other stuff, right? So what does that mean for the pressure? Well, if I know that the total pressure is equal to 1 atmosphere because we're at sea level, how much of that pressure is coming from nitrogen and how much is coming from oxygen? Well, I know that 80% of the particles are nitrogen, which means 80% of the pressure is from nitrogen, right? And so what's my partial pressure of nitrogen here? The pressure of nitrogen is going to be 0.8 atmospheres. In other words, 80% of the air. And then the pressure of O2 is going to be 0.2 atmospheres, right? And then together they would add up to be 1. So you see what I mean? So as long as if you know like the breakdown of the mixture, then we also know the breakdown of the pressure because they're directly related. Okay? So hopefully that makes sense. So what I'm going to do is I'm going to create a practice problem for you right here. And once I create the scenario and kind of give you the overview, pause it, try to do the problem. It's hard, and see how far you can get. When you get stuck, or when you think you get or if you think you have an answer, come back and see how you did. Okay? So here's an example. I'm going to draw a little bit of a setup here. Okay? So this is going to be a container. This is a sealed container. I'm going to create a stopper in the middle. okay? On this side of the container, I'm going to put helium gas. We're going to say that this side is 3 liters, okay? And we're going to say that it's at 1 atmosphere of pressure. On this side, we're going to say we have hydrogen gas. We're going to say this side is 1 liter. And we're going to say that it's at 2 atmospheres of pressure. And right now they're sealed from each other. We're going to say the whole thing is at 25 degrees Celsius. And again, it's a sealed container, so particles will not be going in and out, okay? So this is where we're at initially. So the question I'm going to pose to you is, what is going to be P total, okay, after opening the valve, right? Okay, so basically what I'm going to do is I'm going to open this valve, and we're going to allow these to mix, because they will. Gases fill their container, okay? What is going to be the total pressure of this gas mixture after I open the valve? Okay. Now, I will give you one little hint. It is not just 3 atmospheres, okay? We will need to, this is a mixture, so we will need to address Dalton's law up here. That's true. However, you can't just add 1 and 2 in this scenario here, because remember, this was initially blocked off, okay? The other thing you can assume is that this part, okay, is included in the volume, okay? Like the actual, the tube, okay? So it's included in the volume. Okay, give this a shot. This is a multi-step problem. See how you do, fumble around for a little bit, and then come back. Okay, so we're going to see how you did. The correct answer is 1.25, or I guess 1.3 if we're going to round to sig figs atmospheres. But let's see how we get it. So why can't we just add 1 and 2 together? Well, because the actual volume of the container is changing, which means the pressure is also changing. So what we need to do, and this is how I always work about this, right? If I want P total, that means I need the pressure of the helium and I need the pressure of the hydrogen in order to calculate that, right? This is like how my brain works, go backwards. So I need the pressure of the helium and the pressure of the hydrogen once the valve is open. So I need to figure out what the pressure of helium will be when this valve is open. It's allowed to expand, because it will expand. So it's not going to have 1 atmosphere of pressure anymore. It's going to have less than that because its volume is going to go up. So there's a couple ways you could do this, okay? If you recognized that this was a sealed container and that the temperature was constant, which it is, then you can use Boyle's law, okay? So you can do a quick Boyle's law for helium, right? So if we do it for helium, that would be 1 ATM times 3 liters initially. I don't know my pressure, and my new volume is the total container, which is 4 liters, okay? And that gives you a pressure, suppose it's 3 divided by 4, so that's going to be pressure of 0.75 ATMs, okay? So that's the pressure. I'm just going to put helium here so I remember. So that's the pressure of helium. So now I can do that again. Oops. Okay. And I can say that my initial pressure was 2. My initial volume was 1 liter equals pressure of hydrogen times 4 liters. So my pressure of hydrogen is going to equal 2 over 4, so 0.5 ATMs. Okay. All right. So now we can add these together, right? We can add these together. And P total is 1.25 atmospheres for that. Okay. And I guess actually with sig fig, since we're adding, we're going to keep decimal places, so that's actually good. Okay. So the total pressure of this is going to be 1.25 atmospheres. All right. The other way you could have done this is if you didn't quite pick up on the fact that temp was constant and that container was sealed, so moles is constant, you actually could have done like PV equals nRT and PV equals nRT for each one, and gotten pressure and then added, and you should have gotten the same answer, okay? It just is a little bit extra math, right? You would have put, you would have solved for moles and then gone back and brought moles back in and did it again, okay? Okay, so that's that one. Last piece of info here is going to be Graham's law of effusion. Okay, so we kind of mentioned effusion the other day, but effusion is specifically, it's the diffusion of gases through a small hole. Okay, it's diffusion of gases through a small hole. Smaller things will be able to effuse faster, right? It's just physics, okay? And so there's an actual formula, right, where if you have a gas mixture, like let's say you blew up a balloon and tied it off, and you want to know what's going to come out of that balloon first, right? And by how much, right? Is it going to be the oxygen? Is it going to be CO2? Is it going to be nitrogen, right? There's actually a ratio here. So here's the formula. The rate of gas A, rate is like a speed, right? How fast it's moving, over the rate of gas B equals the square root, okay? Square root of the molar mass of B and the molar mass of A. Okay? So that is, that's it, right? So if you know the ratio of rates, right, and just note here, just be really careful that it's A over B here, but then B over A here. So make sure you have those matching up, right? Okay, let's try one. Let me insert one from the textbook here. There we go. Okay. An unknown gas effuses at a rate that is 0.462 times that of nitrogen at the same temperature. Calculate the molar mass of the unknown gas in grams per mole. Okay. So, we're going to do this, right? Rate of unknown, so we'll just say U over rate nitrogen equals molar mass of nitrogen over molar mass of unknown. Okay, and now we plug in. So it says rate of unknown is 0.462 times that of nitrogen, right? So 462 unknown to nitrogen equals molar mass of nitrogen. So we got to look up that. So nitrogen is 14.01. So this is going to be 28.02 grams per mole of nitrogen over X. Okay? We just got to do algebra. So we're going to square both sides. Okay? 0.462 squared is 0.213 equals 28.02 over X. Okay? And then we'll just manipulate the X around. And so we end up with 28.02 divided by 0.213. And that's going to give us 131.5 grams per mole. And we probably just want 3 sig figs there, so I would just say 132 grams per mole. Okay? Okay. So that is how you do Graham's law, right? So pretty straightforward with that one. Okay. I think that's probably the last one. Whoops. Where are we going here? There we go. Okay, that's probably the last one that we want to talk about. There is one more called root mean square velocity. Okay, and that is one final formula. Okay, so I'm going to give that to you, but we'll talk more about it in class next time. Root mean squared velocity. Root mean is basically like the average speed, right? So this is basically we're going to be calculating like the average speed of the particles at a given temperature. Okay. So remember, it's not kinetic energy, it's speed, and so speed is dependent on molar mass. Okay. Okay. So we use this kind of, it's like mu. It's usually mu RMS. Okay, root mean squared velocity. So mu sub root mean square. Okay, I know it's weird. Go with it. Okay, and here's the formula. It is the square root 3RT over M. And I'll explain what these are. Okay, R is the same gas constant we've been talking about. However, it must be the 8.31 version. Okay, because, well, it's a long story, but those units won't cancel for that, because what we know is basically the 8.31, because it's like an official SI unit with kilopascal pressure, we can actually convert that into kilograms times meters squared over mole Kelvin seconds squared. Okay, I know it's a little bit weird. There's a derivation there, but pressure can be pressure and volume can basically be energy, and then energy can be turned into this, like joule can be turned into this. It's a unit conversion, but it's got to be the 8.31 or else the units don't jive. Okay, temperature has to be Kelvin, and this is M. This is the molar mass. Okay, but the kicker is, because if you look at the R here, it's kilograms per mole, because that's the SI unit. So molar mass has to be in kilogram per mole. Okay, and if you do this right, all the units will cancel, and then you'll square root it, right? So the twos go away here, and you should be left with meters per second, which is the speed. Okay, or the velocity. So if someone's asking you to actually calculate the average speed of, say the nitrogen particles in the atmosphere right now, right? Then as long as you know the temperature and you know that it's nitrogen, you can just plug in and you can actually calculate the velocity that a nitrogen atom is moving at in our atmosphere right now, right? You just plug in room temperature, which is about 300 Kelvin, times R times 3, divided by the molar mass in kilograms per mole. Right, so nitrogen is 28 grams per mole, so that'd be 0.028 kilograms per mole. And then you'd have the speed, okay? That's just a quick way to calculate speed of a gas, okay? I think one of the challenge problems asks you to calculate speed, so that should be helpful, okay? All right, guys, good luck. Have a great weekend, and we'll see you on Monday.